Hello everyone, welcome to my channel Coding Together. My name is Vikas Hoja. Today we will see the disjoint set data structure video part 2. So in this video we will talk about the optimization of the naive implementation of find and union. So if you have not watched the part 1 video, I would recommend you to please go through that video first, then you can continue with this video. I will paste the link of the part 1 video in the description of this video. So let's start with it. So the two optimization techniques are path compression and union by rank. So path compression is applied in the find operation and union by rank is applied in the union operation. So as we know that find of any node, for example 7, means traversing up to the root node from the node itself. So we will move from 7 up the tree to reach the root node. So for 7 the parent is 5, so we'll go to 5. For 5 the parent is 3, so we'll go to 3. From 3 we'll go to 2, and from 2 we'll go to 1, and 1 is the parent of the parent of 1 is 1 itself, so we'll stop here as the root node is 1. So for 7 the root node is 1, so find of 7 will return 1. So as you can see, we are traversing, like we have to traverse from 7 to 5 to 3 to 2 to 1 to reach to the root node. Now the path compression means changing the parent pointer of 7 to the root node. That means the parent of 7 now will become 1. That is the root node. And also the other nodes that we encountered when we traversed up to the root node, like 5, 3, 2, they will also, the parent pointer of all these 3 nodes will also point to the root node, right? Or the parent of all these three nodes as well will be the root node. So what will be the resulting find operation after applying path compression? That's 7, 5, 3, 2. So all the nodes, the parent pointer of all these nodes will point to the root node, or the parent of all these nodes is now the root itself, and the rest of the nodes will be pointing to their parent. There is no change for them. So now if you see, the path has been compressed. The path has been compressed. Next time if we'll do find of 7, then there is no need to traverse from 7 to 5 to 3 to 2 to 1. So they are directly connected to the root, so the traversing calls is saved, right? That is what we call as path compression. Now we will see the union by rank. So union by rank is a optimization technique for the method union, or the operation union. So what it means is that every tree is associated with a rank. So every root element of a tree has a rank associated with it. So rank is nothing but the depth of a tree, level of a tree starting from 0. You can see that for this tree the level is 2. So right, level is 0, 1, 2. So the rank of this root element 1, root for this tree, will be 2, and the rank of this is 1, because the depth is, or the level is 1, 0, 1. Now so what do we do in union by rank? We will move the root of the tree whose rank is smaller under the root of the tree whose rank is greater. So the resultant resultant union will be this. So we have moved a tree, the root, right? The tree or the root with the rank 1 under the root with the rank 2. So in this way, we have not increased the depth of the tree, right? So this is second optimization in the union method. So now if we talk about the time complexity improvement for this path compression and union by rank, so path compression will be log n and union by rank will be log n also. And when they both are used, then the time complexity will be a constant time. Big O of constant. So let's see an example to better understand the path compression and union by rank. So I have taken 10 trees with one node, that is the root node, and the parent pointer is pointing to the root node itself. So we'll start with the first operation, that is union 1 comma 3. So union 1 comma 3 is find 1 union find 3. So as we know, find 1 means finding the root element for 1. So it will be 1 union root element for 3, it will be 3, and 1 comma 3, 1 union 3 will be moving the root element 3 under the root element 1 and changing. So now 3 is the root element 3 is the root 3 is moved under root 1. So the parent of 3 is has now been changed to 1. So we'll change the parent of 3 to 1, and the rank of 1 has increased. Earlier the rank of 1 was 0, now it will be 1. Now we will do union 2 comma 4. So again for 2 comma 4 we will move 4 under 2. So the root element for 4 is 4 and for root element for 2 is 2. So now we have moved 4 under 2. So the parent of 4 has changed to 2 and the rank of 2 has changed from 0 to 1. Now union 3 comma 5. So the root element for 3 is 3 and the root element for 5 is 5, and we'll move 5 under 3. So the parent of 5 has changed from 5 to 3 and the rank of 3 has increased from 0 to 1. Next we will do union 4 comma 6. So here the root element for 4 is 2. The root element for 4 is 2 and the root element for 6 is 6, right? So root element for 4, as we can see, the parent of 4 is 2 and for 2 the parent is 2 itself. So the root element for 4 is 2 and the root element for 6 is 6. Now we have to check the rank of 2 and 6. So the rank of 2 is 1 and rank of 6 is 0. So we will move 6 under 2. So now it will be 2, 4 and 6. So 6 will be moved under 2. Now we'll do union 7 comma 8. So the root element for 7 is 7 and for root element of 8 is 8, and we'll move 8 under 7 and we'll increase the rank of 7 to 1. Now we will perform union 9 comma 8. So the root element for 9 is 9 and the root element of 10 is 10, and we'll move 10 under 9 and will increase the rank of 9 to 1. Now we will do union 5 comma 7. So for the root element of 5 is 3 and root element of 7 is 7, and the rank of 3 and 7, the rank of 3 and 7 is 1 itself, 1 1. So what we will do, we will move 7 under 3, and we will increase the rank of 3 to 2. Now we will do union 6 comma 9. So the root element of 6 is 2 and the root element of 9 is 9, right? So the rank of 2 is 1 and the rank of 9 is also 1. So we will move 9 under 2, and we will increase the rank from 1 to 2. Now the last operation 8 comma 10. So here we have to see carefully that now we'll be applying both the operations, path compression and union by rank, for this last step. How? So if you'll see union 8 comma 10, so union 8 comma 10 means find 8 union find 10 in union 10. So for find 8, it means the finding the root element for 8. So for the 8, the root element is root node is 3. So we'll move 8 directly under 3. So the parent of 8 will become 3. So now we have applied path compression here. So 3, 5, 7 and 8. Right? Now for find of 10, right, we will also apply path compression. So for 10, the root node is 2. So we will move 10 directly under 2. Right? So it will be 2, 4, 6, 9 and 10. And we will now do union of find 8 and find 10. So find 8, so we'll find the root element of it, that is 3, and find of 10, that is root element of it is 2. So we'll check now the rank of 3 and 2. So the rank of 3 and 2 is 2 itself, right? So what we will do, we will move 2 under 3. So 3, 5, 7, 8, 2 and rest of the elements here. Let's see the code for disjoint set union with the optimized find and union operation. So we have taken a parent array, right, which will have the information of the parent pointer representation, and we will have another array, that is rank, that will help us in performing the union by rank. So each root element has the rank associated with it. Now, so rank is the depth of the tree or the levels of the tree. We have a constructor DSU with the parameter size will initialize the parent with the input size, and for will iterate over that size and will initialize the parent of I equal to I. So for at the start, the parent of every node will be the node itself. As we saw that at the start, all the trees or were having one node, that is the root node, and the parent was the root node itself, right? So at the start, all the sets are disjoint sets, and will initialize the rank array with the same size as the input size. Now we will have our find as an optimized solution. So what we have changed here, so earlier we were, when the parent of x was not equal to x, we were doing find parent of x, but now what we will do, we will have the result in the parent of x and will return parent of x when the parent of x is equal to x. So we are changing the parent of the node x plus all the other nodes that we found or we encountered while moving up from that node to the root node. Now the optimized union operation, it takes two parameters x and y. So for x we are finding the root of x, and for y we are finding the root of y. So if the rank of root of x is smaller than the rank of root of y, then we are changing the parent of root of x equal to root of y, right? So we are moving the root element of x under the root of the y by changing the parent of the same. Else if the rank of root of x is greater than rank of root of y, then we'll change the parent of root of y equal to root of x. Else the parent of root of y equal to root of x, and we'll increment the rank of root of x because the root element of y has been moved under root of x. So yes, that's the optimized disjoint set data structure. So I hope you like this video, and if you enjoyed this video, please share and subscribe. Thanks for watching.